Good morning, children. Today we will study the integrated rate law method for the first order reaction. And before that, you study about the zero order reaction. And then we write first the chemical equation, that is A changes to B. Now this is one reaction, and then we can write the concentration of the reactant. The concentration of the reactant at time t0, when the time is 0, then its concentration is represented by A0, and then the concentration of B is 0 because the B is the product. When the reaction is not started, time is equal to 0, then the concentration of the B will be 0. Then we will find out the concentration of reactant after time t. Then after time t, the concentration is represented by A, and then the concentration of represented by B, or you can write Bt, you can write X. So this we can write, or when you write X, then it will be A0 minus X. So I have taken the time at time t0, the concentration of A is 0, and after time t, the concentration of A is A. And then because we need only the concentration of the reactant in the rate law, and that's why we can write the after time t, the concentration of A is A, and the time t0 concentration is A0. Now first we write the rate. The rate of the reaction, the rate is equal to, for first order reaction, the rate is equal to K into A raised to the power 1. A is the concentration after time t, because we have to write the rate. When we write the rate in the differential equation, or we represent the rate is equal to minus dA upon dt, because there is a decrease in the concentration of A. That's why the rate expression for it is the rate is equal to minus dA upon dt. Now we can put value here. If in the rate, then we can write minus dA upon dt is equal to K into A raised to the power 1, that is equal to A. Now it is a differential equation, and now to remove this differential we have to do the integration. Okay? So now this is the differential equation. In this equation we can write minus dA upon dt is equal to K into A, where A is the concentration of the reactant A. Now we write this dA is equal to, this we write minus dA upon A is equal to K into dt. This is the separation of the variable, because we will integrate dA with respect to A and with the dt. So in this way we can write this equation for the rate, and then we integrate it. Now for the integration we can write this minus dA upon A, integrate, then it is equal to K into dt. This equation we can write in the positive form also, that is integration of dA upon A is equal to K into dt when we put minus sign here. Either you can write in this way or you can write in this way. There is only slightly change in the, or you can multiply the whole reaction by the negative sign, then it will become positive and this will become the negative. So this is the rate law for the first order reaction. The A changes into B, and time t0, the concentration of the reactant is equal to A0, and after time t the concentration of A is A. Now when we write the rate law, rate is equal to k into a raised to the power 1. Now the rate is equal to minus dA upon dt. Then we write the rate expression here, minus dA upon dt is equal to k into a, where k is a specific rate constant. Next, because it is differential equation, that's why we have to integrate it, because this is called integrated rate law. So differential can be removed by doing the integration. So now we will do the integration. So in the integration, when we put the minus dA upon a is equal to k into dt. This is the separation of the variable. The dA, the change in the dA divided by a, that is same variables are here. And then it is equal to k into dt. So here we can write the whole equation can be multiplied with the negative sign. Then you will get dA upon a is equal to minus k into dt. So you can write in this way also. So this is the, now we have to do the integration. Now when you do the integration, then this dA upon a will be equal to ln a. The integration of dA upon a is equal to ln a, where ln a is the natural logarithm with the base e. So we can write log e, a, e and log base e, a also. So this is ln a, and then because there the change in the variation in the concentration, and that is the concentration from A0 to A, or you can take with the time t also. So this is equal to, and for the, when we integrate this, then you will get with respect to t, then you will get minus k and t, and again we will put here the limits, that is from 0 to t. Now when you put here, then the limits are here, so we have to integrate within the limit, that is a0 to a. Now we can write here, this is ln a0 minus ln a is equal to minus k into, when t will be t0 to t, so t0 minus, then it is equal to t. Simply the integration of dt will be t, or then when you put the limits here, then 0 to t, at 0 t is equal to 0, and at time t is t, so it is equal to t. So when you integrate this equation, you will be having the value ln a0 minus ln a is equal to k into t. So this is the differential equation for the first order reaction. So ln a is natural logarithm, ln a0 is minus ln a is equal to minus kt. Now we can represent this in ln a0 is equal to minus k into t plus ln a. We can represent in this form also. So we can write here ln a0 now when we integrate this reaction, then we will subtract it from upper limit to lower limit. That means we can write this is ln a minus ln a0. This is equal to minus k, and then we can write t within the limit of t0 to t. So then it is equal to minus kt, because when you put the limit 0 to t, so when this is t0 minus t, then it is equal t minus t0, so then the t0 will be 0, so it is equal to kt. So this will come the equation, this ln a minus ln a0 is equal to minus kt. So this equation, this is the integration of the equation, and this is the expression. Then we can write this ln a is equal to ln a0 minus k into t. And then when you write this is rearrange ln A is equal to minus kt plus ln A0. Now this will become the equation of the straight line. This is ln A is equal to minus kt plus ln A0. So we will plot the graph for the same equation. Then we can convert this ln A, that is natural logarithm, into the log base 10. So when we convert this log base 10, then it will be multiplied by 2.303. So 2.303 into ln A is equal to minus k into t plus log 10. We write the 2.303 into log A0. Now we can write this. This is log A. Now we can write this log A is equal to minus k in upon 2.303 into t plus log A0. You multiply the whole equation by 2.303. So this 2.303 and this 2.303 will be cancelled. And then you can write minus k upon 2.303 into t. So this is a representation of the reaction in the first order reaction. So simply we can write in this way, log A is equal to minus k upon 2.303 t plus log A0. So when we can plot the graphs for the equation, either this ln A is equal to minus kt plus ln A0. And then we can plot the graph for the log A is equal to minus k upon 2.303 into t. So when we plot a graph for the first equation, that is ln A is equal to minus k t plus ln A0. So when we plot a graph, this graph for this side will be ln A, and here we will take the t. This is the equation for first order reaction and the reaction for the straight line. Here we put t is equal to 0. So when you plot a graph, then the graph this point will be ln A0 at time t. ln A0, and then the line will come downward in this way, and then the slope of the line will be equal to minus k. So when we plot a graph for this equation, then you will get one straight line. This is the equation for the straight line, and it will come downward because the slope of the line is minus k. So in this way we can also represent the graph of the line, and then you can represent it. So now we will draw the graph. For the equation Now we will draw the graph for the second equation, that is log A is equal to minus k upon log A is equal to minus k upon 2.303 plus log A0. So this is the second equation. So when you plot a graph for this equation, Again, this is the equation for the straight line. So when we plot a graph for the log A versus t, here this point will be log A0. And then here we write that t is equal to 0. So this concentration will be A0. So again you will get a line that will come downward. And now the slope of the line, slope is equal to minus k upon 2.303. This graph is given in your book also. So this is the representation of the first order reaction. So you will get a graph for it. Now this graph is plotted between log A versus t. So when you plot A versus t, you will get this expression. So now this is the representation of the first order reaction. Now we'll calculate the t half. The time again we can write for the equation. A changes into b. Now the time required, that t here is equal to t half. That is the half of the concentration is converted into the product. Then the A will be equal to A0 upon 2. Clear? And now we can write the equation in this way, that is log A is equal to minus k upon 2.303 plus log A0. This can be written in this way also. We can write as log A minus log A0 is equal to minus k upon 2.303. So this we can write as log A upon A0 is equal to minus k t upon 2.303. In this way we can represent, or we can write for the t half, that is this is equal to, then we can write the value of after time t when it is t half. We can write this t is equal to 2.303 upon k log A0 upon A. Because again you multiply this equation with minus sign, then this will become, when you multiply this equation by the negative sign, then it will be log A0 upon A. We can write here log A0 minus log A is equal to kt upon 2.303. So log A0 upon A is equal to k into t upon 2.303. So in this way we can write that t is equal to 2.303 upon k log A0 upon A. So this is the expression for the first order reaction. Now here we put the t is equal to t half. Here we put t is equal to t half. Then it is equal to 2.303 upon k log A0 upon A0 upon 2. Then you will get this 2.303 upon k log 2, because A0 will be cancelled. So then it is equal to 2.303 log 2 is 0.301 upon k. When you multiply it, then you will get 0.693 upon k. So for the first order reaction, t half is equal to 0.693 3. Now for the first order reaction, the T half is independent of the initial concentration of the reactant, because the concentration term is not here. So the T half is equal to 0.693 upon K. So, and then for the when some questions when the we have to find out the order. So on the basis of this T half, we can say this reaction is first order reaction. When you compare the expression with the zero order reaction, then you can see the difference in the expression. So by the expression or by the T half, because they are in the T half, that is the A0 upon 2K. T half for the zero order reaction is T half is equal to A0 upon 2K. But here the T half is equal to 0.693 upon K, and it is independent of the initial concentration of the reactant. It means when the concentration you are taking the 2 mole per 2 moles, then the T half will be half of this. That is 2 half, that is 1. We can take 100, then it is 50. This is time required for the conversion of the 50 gram. Now we can, whatever the initial concentration is given, when it will become half, then the time is represented as T half. Because the time required for the initial concentration to become half is called as T half. Clear? So because this expression is independent of the initial concentration, that's why you cannot write the concentration here, and that's why it is independent of the initial concentration. So no matter whether you are taking 100 or you are taking 50, you take 5, you can take 7, whatever it be. So the time required for the conversion of half of the reactant into product is called as T half. So this is the expression for the first order reaction. So this I am repeating for the T half. This is the time required for the half of the conversion. Then you have noted down this reaction equal log A is equal to minus K upon 2.303 T log A0. Then we can write in log 0 here. Log A minus log A0 is equal to minus KT upon 2.303. Now we multiply this whole equation by the negative sign. Then you will get log A0 minus log A is equal to KT upon 2.303. Then we can write log A0 upon A is equal to minus KT upon 2.303. So it will become the positive. Log A0 upon A is equal to KT upon 2.303. Now we can write this T is equal to 2.303 upon K log A0 upon A. Then T half is equal to 2.303 upon K log A0 upon A0 upon 2. So the A0 will be cancelled and you will get 2 log 2. So then when this is equal to 2.303 upon K into 0.301, that's it. That is the value of that's the value of log 2. Then it is equal to 0.693 upon K.